Hello, my name is Fischer. I'm a PhD student at Valeo in Kronach, Germany, in cooperation with the Technical University of Ilmenau. Today I'm going to present to you our newest work entitled MagneticPillars, efficient point cloud registration through hierarchized bird's-eye view cell correspondence refinement. First we will start with the motivation and general idea of the paper. The aim of point cloud registration is to determine a transformation matrix which transforms one point cloud into the reference frame of another cloud, forcing them to overlap. Recent point cloud registration algorithms often utilize a hierarchical post-refinement processing, where initial correspondences are found in a set of subsampled superpoints, which are subsequently refined on a finer scale. Since point clouds are usually displayed in an unordered fashion, such methods often conduct 3D-sensitive convolution approaches for feature generation. However, in order to establish affiliations between the initial subsampled superpoint correspondences and the respective points of the cloud's original scale, expensive grouping mechanisms like nearest neighbor search have to be applied, which increase the overall complexity of the methods. Furthermore, recent works often rely on subsequent outlier filtering by methods like RANSAC due to deficient point correspondence predictions, which again leads to an increase in runtime. For application fields like autonomous driving tasks where certain runtime requirements have to be fulfilled, the increased computational effort of those methods impedes their application in those scenarios. So to overcome these challenges, we present MagneticPillars, a robust and lightweight point cloud registration algorithm based on hierarchized 2D bird's-eye view cell correspondence refinement. In this context, the necessary correspondences between the point clouds are determined on planar projections of the clouds, with subsequent pose estimation based on 3D pillar centroids. Processing the cloud data in a rasterized grid results in fixed affiliations between the cells on the coarse and fine scale, leading to a massive improvement in runtime, since no expensive grouping mechanisms have to be conducted. To ensure a stabilized training process, we apply a novel coarse and fine grid cell matching loss, resulting in robust point matches where a minimal amount of key points is already sufficient to determine an accurate pose. We conduct a wide range of experiments for our use case of autonomous driving scenarios on the two datasets Kitty and New Scenes, where we outperform state-of-the-art methods with respect to pose estimation accuracy and overall runtime. On this slide, you can see an overview of the overall processing pipeline of our approach. We start with a feature generation module which is based on voxel-wise point aggregation and encoding, with a subsequent accumulation in the height dimension to generate pillar-shaped features for the bird's-eye view representation. In a unit-like fashion, we first downsample the resulting grid features to generate initial coarse cell matches. These are afterwards upsampled to the original resolution for the fine scale correspondence estimation. Pillar centroids are determined for each of the fine cell matches, which are finally used within a pose estimator like singular value decomposition to generate the 3D pose. In the following slides, we will cover a more detailed presentation of each of the processing modules. First, the point cloud is being voxelized, with all points associated to a certain voxel, as well as the voxel centers being saved for the further processing. Subsequently, the x, y, and z coordinates of the voxel points are normalized by the 3D coordinates of the voxel centers. We use a separated processing of local and global cloud information. In this context, the normalized x, y, and z coordinates with the intensity values are encoded by the pillar encoder for local features, and the voxel centers get encoded by the positional encoder to generate global feature descriptors. Finally, voxel descriptors which share the same coordinates in width and height direction of the grid are vertically accumulated. This results in c times d dimensional features for a 2D bird's-eye view grid representation with dimensions h and w. Following a unit-like encoder-decoder architecture, we first downsample our grid applying multiple double convolution layers, with max pooling for dimension reduction. On the lowest scale, multiple self and cross-attention layers are used to determine the initial coarse cell correspondences. The coarse scale features are now upsampled via double convolutions and bilinear interpolation to recover the original grid resolution. Since direct associations between cells of the coarse and fine resolutions can be obtained, there is no need for expensive grouping mechanisms used in other methods to establish the necessary coarse to fine correspondences. This leads to a tremendous reduction of computational complexity. To generate connections in between the fine cells of the point clouds, cross-attention is applied on the fine grid cells, initialized per the previously determined coarse cell matches. Now, in order to be able to recover a 3D pose from the generated correspondences, we need to pass three-dimensional point coordinates to a pose estimator like singular value decomposition. Therefore, for each of the grid cells featured in the set of correspondences, we calculate the pillar centroids by averaging the global 3D coordinates of all points which were aggregated by the voxels in step 1, associated to the respective pillars. Finally, using the 3D point correspondences with their confidences generated by our network, we can perform pose estimation via an arbitrary 3D transformation solver, like SVD. We follow the same data preprocessing as conducted by the compared state-of-the-art methods, where frame pairs are selected which are at least 10 meters apart. We use the two autonomous driving datasets Kitty and Nuisance for performance validation, since they provide ground truth poses for the respective LiDAR point clouds. Again, according to the previous methods, ICP is applied on the ground truth poses to counteract possible drifts. Here we want to note that no ICP refinement is ever performed on any of the predicted poses by our network in any of the experiments. We train our network for 100 epochs using Atom Optimizer and our novel coarse and fine cell matching losses. We compare magnetic pillars to recent state-of-the-art point cloud registration methods using relative translation and rotation error, as well as registration recall with thresholds of 0.6 meters for translation and 5 degrees for rotation. Furthermore, we report the average runtime for each approach. We evaluate our approach based on the mentioned metrics and frame pairs on the Kitty and Nuisance datasets for different number of extracted key points and registration backends. Generally, we are able to outperform all state-of-the-art methods or gain comparable results while being able to feature a much lower overall runtime due to our efficient 2D correspondence search. Most comparable to our performance are the works of GeoTransformer and Predator, which either show double the model inference time or heavily rely on outlier filtering by expensive optimization backends like RANSAC. In contrast, MagneticPillars is able to generate robust point correspondences, where even a small amount of extracted key points is already sufficient to perform an accurate pose estimation. As visualized in the image, green lines represent correctly detected correspondences and red lines false ones. Moreover, the inlier ratio IR expresses the percentage of correctly determined matches. Finally, we want to display the generalizability of our approach by applying it on frame pairs with distances of 15 meters and 20 meters, which were not included in the training process. While the performance of the compared methods drastically decreases, especially using SVD as backend without iterative optimization, MagneticPillars is generally able to maintain a decent pose estimation performance. For further details, we encourage you to check the paper. Thank you for your attention.